Okay, so we're going to do problem number 16 in chapter 6. And in this problem, hopefully you've read it by now, but we're going to figure out the speed of which car A hit car B depending on the kinetic friction. So in our free body diagram, we have normal force in the y direction, friction force in the x direction, and we also have gravity. But because we have a different reference frame, we're going to have to break the components of gravity into x and y. So using SOHCAHTOA, we can figure out that in the x direction we have Fg sine theta, and in the y direction we have Fg cosine theta. And this will be accelerating downwards, down the hill. So for our derivation, we're going to figure out what velocity will be. So first, in the x direction, we have F net equals mass times acceleration, which is just Newton's second law. Our x forces will be Fg sine theta and friction force. And we know that Fg sine theta will be bigger because we're accelerating down the hill. So that would imply that Fg sine theta is bigger than the friction force. So we have Fg sine theta minus friction force equals mass times acceleration using Newton's second law. And next we just solve for acceleration. We will use this later in one of the kinematic equations when we need acceleration. We're going to rewrite some of the terms. We know that Fg will equal to mass times gravity, that's Newton's second law, and we know that friction force is equal to mu, or the kinetic friction, times normal force. In the y direction, there is no acceleration because it's only accelerating down the hill in the x direction. So we know F net for the y direction will equal 0, and when the F net equals 0, we know that all the forces will cancel out. So in our free body diagram, our y forces will be normal force and Fg cosine theta, and they must be equal in order to cancel out and equal 0. So we have normal force equals force of gravity times cosine theta, is equivalent, which is also equivalent to mass times gravity times cosine theta. Now we're going to take all the stuff we just rewrote and all the different forces, and we're going to plug them back into the equation in step 3 for acceleration. So we figured out what Fg was, and we figured out what friction force was. So when we rewrite it, it should look like acceleration equals mass times gravity, which is force of gravity, times sine theta minus mu times mass times gravity cosine theta all over m. And then next we'll divide everything by m just to simplify everything out. And now we're going to recall one of the kinematic equations for constant acceleration. We're going to use v squared equals v naught squared plus 2 times acceleration times the distance. We're going to plug the equation we found for acceleration over here, the simplified version. We're going to plug that into the kinematic equation for a. So we should get v squared equals v naught squared plus 2 times the distance times g sine theta minus mu g cosine theta. And we're going to square root both sides so we can isolate velocity. Now we're going to solve. We're going to plug in all the information, and we're going to do part A. So in the equation, you're given that initial velocity is 16 meters per second. The distance is 23.5 meters. The angle is 12 degrees, and also the coefficient of kinetic friction will be 0.6 for part A. So when you plug all that info into this equation, it should look like this. And once you plug it into your calculator, you should get 9.02 meters per second. For part B, it's pretty much the same thing. They give you a new kinetic friction, and they ask for the speed or the velocity. And you plug it all back in again using the given data, and you should get 17.5 meters per second. And that's how you do question 16.